Hello everyone. Today, let's continue with functions. First of all, let me introduce one-to-one function. So, a function f from a to b is called a one-to-one function. Or an injection. One-to-one function is the same as injection. If I say a function is one-to-one, it's the same as saying the function is an injection. If I say a function is an injection, that's the same as saying the function is one-to-one. So a function f from a to b is called a one-to-one function if for all s1, x2 in a domain s1 not equal to s2 implies f of s1 not equal to f of s2. This definition says if f is a one-to-one function, then f assigns every element in the domain to a different element in the codomain. This definition says if f is one-to-one, f assigns every element in the domain to a different element in the codomain. Let me show you the picture. That's just an example. Let me show you an example with picture. Say let's set A. Let's set B. Set A has 4 elements: A, B, C, D. Set B also has 4 elements: A, B, C, D. F assign A to A, B to B, C to C, D to D. So F assign every element to a different element. F assign every element in set A to a different element in set B. This F is one-to-one. F assign every element to a different element. This F is one-to-one. But another example, let me show another example. Set A, set B. Set A has 4 elements: A, B, C, D. Set B has 4 elements: A, B, C, D. If F assign A to A, B to B, C to D, and D to D, then this function is not one-to-one because both C and D, F assign both C and D to the same element D here. This is not one-to-one. F assign 2 different elements to the same element here. If F assigns C and D to the same element in a codomain, then this F is not one-to-one. So if F assigns every element in the domain to a different element in the codomain, then F is one-to-one. But if F assigns any two elements in a domain to the same element in the codomain, then F is not one-to-one. So keep this idea in mind. Note. If F assigns every element in the domain to a different element in the codomain, then F is 1-to-1. If F assigns every element in the domain to a different element in the codomain, then F is 1-to-1. But if F assigns any two elements in the domain to the same element in the codomain, then F is not 1-to-1. If F assigns every element in the domain to a different element in the codomain, then F is 1-to-1, like this example here. But if F assigns any two elements in the domain to the same element in the codomain, like this example, if F assigns any two elements in the domain to the same element in the codomain, then F is not 1-to-1. Now, to prove F is 1-to-1, how do we prove F is 1-to-1? To prove F is 1-to-1, we need to use this definition. But to show something not equal to each other is not easy. So we try to use the contrapassive of this statement. The contrapassive of this statement can be written as F of S1 equal to F of S2 implies S1 equal to S2. This is the contrapassive of this statement. They are equivalent. Using this statement is easier to write a proof. So keep this in mind. To show F from A to B is 1-to-1, we need to show that for all S1, S2 in the domain F of S1 equal to F of S2 implies S1 equal to S2. That's how we show F is 1-to-1. To show F is not 1-to-1, we need to show F assign any two elements in the domain to the same element in the codomain. So we can use the negation of this statement. To show F from A to B is not 1-to-1, we need to show that there is a x1, x2 in the domain, the negation of this statement. There is s1, s2 in the domain such that f of s1 equal to f of s2, but s1 is not the same as s2. The negation of a statement. There is s1, s2 in the domain such that f of s1 equal to f of s2 and s1 not equal to s2. This statement is the negation of this statement here. Going for the negation, for all s1, s2 become there exists s1, s2. Then when we negate the statement, P implies Q. When we negate the statement, P implies Q, that's equivalent to not P or Q. P implies Q is the same as not P or Q. Apply De Morgan's law, that's equivalent to P and not Q. If we treat this as P, this as Q, we have P and not Q. So the negation of this statement says there exists S1, S2 in the domain such that f of S1 equal to f of S2 and S1 not equal to S2. So to show a function is one-to-one, we need to prove it for all S1, S2. F of S1 equal to f of S2 implies S1 equal to S2. But to show a function is not one-to-one, we just need to give one example for S1, S2, such that f of S1 equal to f of S2 and S1 not equal to S2. That's the meaning of one-to-one function, and that's how we use it to prove a function is one-to-one or not. Next, let's do some proof about one-to-one functions. For each of the following functions, determine whether it's one-to-one. First example, let f from real number to real number be defined as f of x equal to 3x plus 1. Determine whether this function is one-to-one. If f assign every element in the domain to a different element in the codomain, then f is one-to-one. But if f assign any two elements in the domain to the same element in the codomain, then f is not one-to-one. Let's try to plug in some numbers. If I plug in 1, I get 4. If I plug in 2, I get 7. If I plug in 3, I get 10. If I plug in 4, I get 13. It looks like f assign every element in a domain to a different element in the codomain. So let's try to prove it. It looks like this function is one-to-one. So let's try to prove it. So to prove it, we use this definition here. This is equivalent to the definition of one-to-one function. This statement is equivalent to the definition of one-to-one function. So let's use this statement to prove f is one-to-one. So prove it. Let S1, X2 belong to the domain. Let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. Assume f of S1 equal to f of S2. Then I substitute S1 to the function, and I substitute x2 into the function. I have 3s1 plus 1 equal to 3s2 plus 2. I try to prove s1 equal to s2. So I can subtract 1 from both sides. I get 3s1 equal to 3x2. Then I can divide both sides by 3. I get s1 equal to s2. So f is one-to-one. By this definition, by this statement, f is one-to-one. Next example. Let f from real number to real number be defined as f of x equal to 4x squared plus 1. Is this function one-to-one? If f assign every element in the domain to different elements in the codomain, then f is one-to-one. But if f assign any two elements in the domain to the same element in the codomain, then f is not one-to-one. If f assign any two elements in the domain to the same element in the codomain, then f is not one-to-one. Let's check. If I plug in, let's try some values. If I plug in -1, if I substitute -1 for x, I have 4 times -1 squared plus 1, which is 5. If I substitute 1 for x, I also get 5. So we can see that here, f assign two different elements in a domain to the same element in the codomain. This function f is not one-to-one. So let's write a proof. So to show f is not one-to-one, give an example. There is s1, s2 in the domain, such that this statement f of s1 equal to f of s2, and s1 is not the same as s2. So let's give an example. So let s1 equal to -1, s2 equal to -2, so equal to +1 in a domain. Domain is all real number, the set of all real number. Then f of s1 equal to 4 times f of s1 equal to f of -1 equal to 4 times -1 squared plus 1, that equal to 5. F of s2 equal to f of +1, that's 4 times 1 squared plus 1 equal to 5. So we see f assign two different elements in a domain to the same element in the codomain. We see f is not one-to-one. So we can say, since f of s1 equal to f of s2, but s1 is not the same as s2, then f is not one-to-one. We use this statement to show f is not one-to-one. Next example. Let f from real number to real number be defined as f of x equal to the floor function of x over 3. Let f from real number to real number be defined as fx equal to x over 3. Floor function of x over 3. Is this function one-to-one? If f assign every element in the domain to a different element in the codomain, then it's one-to-one. Otherwise, it's not one-to-one. Let's try some values. If I substitute 1 for x, I get 1/3. Floor function of 1/3 is 0. If I substitute 2 for x, floor function of 2/3 is also 0. Since f assign 1 and 2, both 1 and 2 to 0, f is not one-to-one. F assign two different values in the domain to the same value in the codomain. F is not one-to-one. So here we can see that f is not one-to-one. So let x1 equal to 1, x2 equal to 2 in the domain. Let s1 equal to 1, s2 equal to 2 in the domain. Then f of s1 equal to f of 1, which is floor function of 1/3, that equal to 0. F of s2 equal to f of 2, that's floor function of 2/3, which is also 0. Since f assign two different values in the codomain, in the domain to the same value in the codomain, f is not one-to-one. So since f of s1 equal to f of s2, f of s1 equal to f of s2, but s1 is not the same as s2, then f is not one-to-one. Next example. Let f from real number to real number be defined as f of x equal to the floor function of 2x. Is this function one-to-one? Let's try some different values. If f assign every element in the domain to a different element in the codomain, then f is 1 to 1. But if f assign any two elements in the domain to the same element in the codomain, then f is not 1 to 1. Let's try some values here. Try to plug in some values for x. If I substitute 1, 2 times 1 is 2. Floor function of 2 is 2. F of 1 is 2. If I substitute 2, f of 2 is 4. If I substitute 3, f of 3 is 6. It looks like f is 1 to 1, but be careful, be very, very careful. The domain is the set of real number, not only whole number. It may be decimal number, it may be fractions, not only whole numbers. It works for whole number. Now let's try some decimal numbers. If I plug in 0.1 for x, 2 times 0.1 is 0.2. Floor function of 0.2 is 0. If I substitute 0.2 for x, 2 times 0.2 is 0.4. Floor function of 0.4 is also 0. So f assign two different elements in the domain to the same element in the codomain. This f is not 1 to 1. So be very, very careful here. Real number contains not only whole number, it may contain decimal number and fractions. So let s1 equal to 0.1, x2 equal to 0.2 in a domain. F of s1 equal to f of 0.1, which is floor function of 2 times 0.1 is 0.2, which is 0. F of s2 is f of 0.2. If I substitute 0.2, I have floor function of 0.4, which is also 0. Since f of s1 equal to f of s2, but s1 is not the same as s2, then we can say that f is not 1 to 1. If f assign two different elements in the domain to the same element in the codomain, f is not 1 to 1. Next, let f from z to z be defined as f of x equal to the floor function of 2x. Here, z stands for integers, r stands for all real number, z stands for the set of integers. If we only consider integers, let's try to plug in some integers, see what we get. If I substitute 1, f of 1 is floor function of 2. Floor function of 2 is 2. Floor function of any whole number stays the same. If I substitute 2, f of 2 is 4. F of 3 is 6. So it looks like that f assign every element in the domain to a different element in the codomain. So it looks like f may be 1 to 1. Let's try to prove it. So let x1, x2 belong to the domain. Assume f of s1 equal to f of s2. Then we substitute s1, substitute x2. We have floor function of 2s1 equal to floor function of 2s2. And since we know x1, s2, they are both integers, floor function of integer is the same, stays the same. Since 2s1 and 2s2, they are both integers, then floor function of integer stays the same. since they are both integers, floor function of integers stays the same. Then I can divide both sides by 2. S1 equal to S2. So f is 1 to 1. Next, let f from 0 to infinity to real number be defined as f of x equal to x squared. Determine whether this function is 1 to 1. So for s squared, we know if I plug in positive 1, negative 1, I get 1. I get 1 for both numbers. If I plug in positive 1 or negative 1, I get 1. But the thing is, our domain is from 0 to infinity. We are not allowed to plug in negative 1. If we only consider positive 1, if we only consider positive numbers, when I plug in 1, I get 1. When I plug in 2, I get 4. When I plug in 3, we get 9. It looks like f assigns every element in the domain to a different element in the codomain. So it looks like this f is 1 to 1. So let's try to prove it. So let S1, S2 belong to the domain. Let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. Then we substitute S1 at X2. Then we have X1 squared equal to X2 squared. In general, when we take square root, the answer could be either positive or negative on both sides. But here, since we only consider positive number, remember for positive number, if x is greater than 0, then square root of x squared is always the same as x. If x is greater or equal to 0, square root of x is always the same as x. If x is less than 0, then square root of x squared is negative x. In our situation, we only consider positive. In our situation, we only consider positive numbers. Both S1 and S2 are non-negative. So if I take square root, they stay the same. Take square root on both sides. I have square root of x1 squared equal to square root of x2 squared. And since they are both positive, since both S1 and S2 are positive, so square root of S1 squared equal to S1. Square root of S2 squared equal to S2. So f is 1 to 1. Next, let me introduce onto function. A function f from a to b is called a onto function. Or a surjection. A function from a to b is called onto function or surjection. Surjection is the same as onto function. If we say the function is onto, it's the same as saying the function is a surjection. So onto function and surjection is the same. A function f from a to b is called onto function if for all y in B there exists a x in A such that f of x equal to y. This definition says for every element in the codomain there is an inverse image of such that f of x equal to y. For every y in the codomain, For every y in the codomain, there exists an inverse image in a domain such that f of x equal to y. For all y in the codomain, there exists an x in the domain such that f of x equal to y. This x is called an inverse image of y. So note, if every element in the codomain has an inverse image, then the function is onto. If every element in the codomain has an inverse image, then the function is onto. Let me show you some example here. So, say set A contains 4 elements, A, B, C, D. Set B contains 3 elements, A, B, C. Assume F assign A to A, assign B to B, assign C to C, assign D to C. We know this function is not one-to-one, but every element in the codomain has an inverse image. Inverse image of A is A. Inverse image of B is B. Inverse image of C is both C and D. So, if every element in the codomain has an inverse image, this function is onto. So, this function f is onto. This function f is onto. Let's look at another example. F assign every element in A to B. F is a function from A to B. Set A contains 4 elements, A, B, C, D. Set B contains 3 elements, A, B, C. F assign A to A, B to A, C to C, D to D. Is this function onto? Now for A in the codomain, it has 2 inverse images, A and B. For C in B, it also has 2 inverse images, C and D. But for element B in set B, it doesn't have an inverse image. So if any element doesn't have an inverse image, then this function f is not onto. If every element in the codomain has an inverse image, then the function is onto. But if any element doesn't have an inverse image, then the function is not onto. If every element in the codomain has an inverse image, then the function is onto. But if any element doesn't have an inverse image, then it's not onto. Next, let me introduce a theorem. Let f from A to B be a function. Then f is onto if and only if the image of the domain equal to B. F is onto if and only if the image of a domain is B. image of the domain is the set of all possible outcomes that f can have. So this is the range of f. Image of the domain is the set of all possible outcomes that f can have. So this is the range of f. F of A is the range of f. By definition, if f is a function from A to B, image of A, f of A, the image of A is the set of all y in B such that y equal to f of x for some x in A. That's how we define image of a set. Image of set A is the set of all y in B such that f of y equal to f of x for some x in A. So that's what f of A means. Next, let's try to prove it. This statement is an if and only if statement. We need to prove these two statements, they are equivalent. So we need to assume left side, prove for the right side. Then assume the right side, prove the left side. This is an if and only if statement. We need to prove in both directions. So prove. Let's first of all assume f is on 2. Assume f is on 2. We want to prove f of A equal to B. We want to prove f of A equal to B. By its definition, f of A is the set of all y in B. So every element in f of A belongs to B. By its definition, f of A is a subset of B. So by definition of f of A, f of A is a subset of B. To show two sets equal, we must show that they are subsets of each other. We know f of A is a subset of B. Next, we try to show B is a subset of f of A. That means we try to show every element in B belongs to f of A. So let y belong to B. Let y belong to B. In order to show B is a subset of f of A, we need to prove that y eventually belongs to f of A. That's our goal. We try to show B is a subset of f of A. That means we need to show every element in B belongs to f of A. Let y belong to B. Then since f is on 2, what does it tell us? Since f is on 2, what does it tell us? If f is on 2, that means for all y in B, there is a x in A such that f of x equal to y. So since f is on 2, for this y in B, there is x in A such that f of x equal to y. This is equivalent to this statement. This is equivalent to this statement. So observe this statement. There is x in A. F of x equal to y. It's the same as y equal to f of x for some x in A. These two statements are equivalent. So we can say that y equal to f of x for some x in A. Since y satisfies this condition, so we say y belongs to the set f of A. So y belongs to the set of f of A. Since for all y in B, y belongs to f of A, that means every element in B belongs to f of A. So B is a subset of f of A. And since they are subsets of each other, we can say they are the same. So f of A equal to B. That's one deduction. Assume left side, proof for the right side. Next, we assume the right side, proof for the left side. The other deduction from right to left. We assume f of A equal to B. Assume f of A equal to B. We try to prove f is onto. So try to prove for all y in B, there's x in A, such that f of x equal to y. So let y belong to B. Let y belong to B. Since set B is the same as f of A, then y belong to f of A. Let y belong to B. Since B is the same as f of A, then y belong to f of A. Since y belong to f of A, it satisfies this condition. So y equal to f of x for some x in A. And we know this statement is equivalent to this statement. F of x, y equal to f of x for some x in A is equivalent to the statement there is x in A, such that f of x equal to y. These two statements are equivalent. So that means there is a x in A such that f of x equal to y. Therefore, f is onto. For all y in B, there's x in A, such that f of x in y. So f is onto. For all y in B, there's x in A, such that f of x equal to y. So f is onto. So that's the proof in both deductions. F is onto if and only if the range of f equal to the codomain of f. That's the proof. Next, let me show you how to determine if a function is onto. So let f be a function from A to B. Note, if the range of f is the same as the codomain, then f is onto. If the range of f is not the same as the codomain, then f is not onto. And to prove f is onto, to show a function f is onto, we need to use definition. We need to show that for all y in B, there is an x in A, such that f of x equal to y. To show f is not onto, we need to show that we need to use the opposite of the definition. Show that there is a y in B such that for all x in A, f of x not equal to y. So to show f is not onto, we show the opposite of the definition. Next, let's do some problems about onto functions. For each of the following functions, determine whether it's onto. For each of the following functions, determine whether it's onto. First example, let f from real number to real number be defined as f of x equal to x plus 3. Is this the onto function? The codomain is the set of all real numbers. Now how about the range? If I plug in a very, very large number, f of x could be very, very large. If I plug in a very, very large negative number, f of x will be very, very large negative number. So the range is actually the set of all real number. The range could be all real number. So it looks like the range is the same as codomain. If the range is the same as codomain, this function is onto function. Now let's draw a proof. So it looks like this function is the onto function. Let's draw a proof. Use definition, draw a proof. So let y belong to the range. Sorry, let y belong to the codomain. Let y belong to the codomain. We try to find x in the domain such that f of x equal to y. So in order to find x, I do this. Let f of x equal to y. Then we have x plus 3 equal to y. In order to get x by itself, I subtract 3 from both sides, x equal to y minus 3. So for all y, I can find x here. Let x equal to y minus 3. A real number minus 3 is also a real number. So for all y, I can find a corresponding x. For all y, I can find corresponding x. And then f of x equal to f of y minus 3. If I substitute y minus 3 for x, I have y minus 3 plus 3, which equal to y. So for all y, there's x. For all y in the codomain, there's x in the domain, such that f of x equal to y. That's the proof that f is onto. So f is onto. So f is onto. This is your scratch work. We don't need this. We don't need this as part of the answer. This is your scratch work. This work help you to find an x here. That's your scratch work. Another example. Let f from real number to real number be defined as f of x equal to 2 to the power x. Is this an onto function? The codomain is the set of all real numbers. How about the range? 2 to the power x, exponential function is always positive. 2 to the power x is an exponential function that's always positive. It cannot be 0 or negative. So we know 0. It cannot be 0 or negative. So we know that the range contains only positive number, which is not the same as the codomain. The range contains only positive number, which is not the same as the codomain. So we know this function is not onto. How do we prove this function is not onto? Give an example. Use the opposite of definition. Give an example. So we know this function cannot be 0. Exponential function cannot be 0. So let y equal to 0. That belong to the codomain. Let y equal to 0. That belong to the codomain. We try to show that for all x, f of x doesn't equal to y. We know f of x equal to 2 to the power x, which is always greater than 0. So f of x cannot be 0 for all y, for all x. So f of x doesn't equal to y because y is 0 for all x. So f is not onto. So to show a function is onto, use definition to prove it is onto. For all y, find x, then make f of x equal to y. To show a function is not onto, give an example, find a y, then make the function not equal to y for all x. Next example, let f from real number to real number be defined as f of x equal to x squared. Is this function an onto function? Is this function an onto function? So to determine if a function is an onto function, we try to compare the range and the codomain. If they are the same, then the function is onto. If they are not the same, the function is not onto. So the codomain here is the set of all real numbers. What's the range? Look at the function s squared. S squared can only be positive. The range is the set of all possible outcomes. So the only positive outcome is 0 or positive numbers. The only possible outcome is 0 or positive numbers. The range only contains 0 or positive number, which is not the same as the codomain. So we know this function is not onto. To show a function is not onto, we'll give an example. So let y equal to, we know this function cannot be negative number. S squared cannot be negative number. So give an example, let y equal to -1. Then f of x equal to x squared. S squared is always greater than or equal to 0 for all x in the domain. So that means f of x cannot be -1. Something greater than 0 cannot be -1. So f of x cannot be -1 for all x in the domain. So f of x doesn't equal to y. Doesn't equal to this y for all x in a domain. So f is not onto. Next example. Let f from the set of all real number to the interval from 0 to infinity be defined as f of x equal to x squared. Now is this function onto? Is this function onto? Let's compare the codomain and the range. Here the codomain is the interval from 0 to infinity including 0. What's the range? What's the range here? The range is the set of all possible outcomes. X squared is always 0 or greater than 0. X squared is always 0 or greater than 0. So the range is the same as the codomain. So this function is onto function. The range is the same as codomain. This function is onto. To show it's onto, we need to prove it, use definition. So let y belong to the codomain. For all y in the codomain, we try to find x in the domain. What can we find x in the domain? To find x in the domain, we let f of x equal to y, then s squared equal to y. Then I can take square root. Take square root. Since y is always positive, I take square root. I can take x equal to square root of y. Y is always positive. Y belongs to the interval from 0 to infinity. Y is always positive. So I'm allowed to take square root. Let s equal to square root of y. So for all y in the codomain, let x equal to square root of y. Square root of positive number is a real number. So let s equal to square root of y. Let belong to the domain. Then f of x equal to f of square root of y. We substitute square root of y for x. I have square root of y squared, which is y. So for all y in the codomain, there's an x in the domain. For all y in the codomain, there's x in the domain such that f of x equal to y. So f is onto. That's the proof that f is onto function. This is your scratch work. Next example. Let f from real number to real number be defined as f of x equal to the floor function of 2x. Is this function an onto function? Is this function an onto function? Let's compare the range and the codomain. The codomain is the set of all real numbers. How about the range? How about the range? Range represents a set of all possible outcomes. When you take floor function, the set of all possible outcomes is integers. You won't get decimal number when you take floor function. So the range only contains integers, but the codomain is the set of all real numbers. So they are not the same. This function is not onto function. This function is not onto function. So let's write a proof to show that this function is not onto function. So to show a function is not onto function, give a example. Let's call counter example. So no, this function cannot be a decimal number. So let y equal to, say, half. That belong to the codomain. Let y equal to half belong to the codomain. Then we try to show that f of x doesn't equal to y. We know f of x equal to the floor function of x. It must be an integer. The floor function of 2x must be an integer for all x. So f of x cannot be a half for all x. So f of x doesn't equal to y. Half is y for all x. So f is not onto. To show a function is not onto, give an example. Find a y in the codomain and try to show that f of x doesn't equal to y for all x. Same thing from the previous example. Find a y in the codomain. Here, codomain is the set of all real numbers. Find a y in the codomain such that f of x doesn't equal to y for all x. Then f is not onto. Next example. let f from real number to integer. Z stands for integer. Let f from real number to integer be defined as f of x equal to the floor function of 2x. For the same function, if I change the codomain to the set of all integers, for the same function, if I change the codomain to the set of all integers, now it's the function onto. It's the function onto. It looks like when we take floor function for real number, the outcome is outcome is a set of integers. So it looks like the codomain and the range is the same. When we take floor function for real numbers, we get a set of all integers. So it looks like the codomain and the range is the same. So the function is onto. Let's try to prove it. So use definition for all y in a codomain. Let y belong to the codomain. We try to find an x. In a domain. Let's make f of x equal to y. So we know floor function of integer stays the same. Ceiling of floor function of integer stays the same. So if I can make 2x to be an integer, floor function of 2x is the same as 2x. So we want to make y, f of x equal to y. We want to make f of x equal to y. That means we want to make floor function of 2x equal to y. So to make it easier, if I can make 2x to be integer, then floor function of 2x will be the same as y. So I want to make if I can make 2x equal to y, then floor function of 2x equal to y. So I try to make 2x equal to y. That means x equal to y over 2. That means if I make y over 2, it satisfies f of x equal to y. And y is an integer. Integer over 2 is a real number. So this is your scratch work. Let y equal to, let y be any integers. Let z equal to, let x equal to y over 2. Let belong to the domain. Let z equal to y over 2. Let belong to the domain. Then we try to show f of x equal to y. F of x equal to f of y over 2. We substitute y over 2 for x. That's floor function of 2 times y over 2, which is the floor function of y. Since y is an integer, floor function of y stays the same as y. So I prove that f of x equal to y. So f is onto. Next example. Let f from integer to integer be defined as f of x equal to the floor function of 2x. Now if I change the domain to be integer, is this function onto? To verify if a function is onto function, we try to compare the codomain and the range. Here the codomain is the set of all integers. How about the range? The domain is the set of all integers. Let's try to plug inside integer, see how the range looks like. If I plug in 0 for x, I get 0. If I plug in 1 for x, I get 2. If I plug in 2 for x, I get 4. If I plug in 3, I get 6. So it looks like the range only contains even numbers. So the range is not the same as the codomain. This function is not onto. To show a function is not onto, we give a counterexample. So let y equal to 1. We know the range contains only even number. Y is not in the range. Let y equal to 1. Let belong to the codomain. Let y equal to 1. Let belong to the codomain. F of x equal to the floor function of 2x. And we know domain contains only integer. If I plug in integer, 2 times integer is integer. So f of x equal to floor function of 2x. That equal to 2x for all x in the domain. That equal to 2x for all x in the domain. And 2 times integer is always even. Two times integer is always even. So f of x cannot equal to y. Because y is number 1. 1 is not even. So f of x doesn't equal to y for all x in the domain. So f is not onto. Next, let f from integer to integer be defined as f of x equal to the floor function of x over 3. Is this function an onto function? Let's compare the codomain and range. If the codomain is the same as the range, then the function is onto. Otherwise, the function is not onto. The codomain contains the set of all integers. How about the range? Can we obtain all integers by plugging integers? If I substitute 0, I get 0. If I substitute 1, I get 0. If I substitute 2, I get 0. If I substitute 3, I get 1. If I substitute 6, I can get 2. If I substitute 9, I can get 3. It looks like the range contains the set of all integers. So it looks like the range contains the set of all integers. So it looks like this function is onto. Let's prove this function is onto. Let y belong to the codomain. Let y. We try to show for all y in the codomain there's x, such that f of x equal to y. Let y belong to the codomain. We try to find x such that f of x equal to y. F of x is the floor function of x over 3 equal to y. And if I can make x over 3 to be an integer, then floor function of integer is the same as the number itself. So if I make x over 3 equal to y, then x over 3 is an integer. Floor function of integer stays the same. Then I have x over 3 equal to y. I can multiply both sides by 3. That means I can make x equal to 3y. Y is an integer. 3 times integer is also an integer. So this x is an integer. So for all y in Z, the s equal to 3y. Then 3y times 3 times the integer is an integer. So the x equal to 3y belong to the domain. Then f of x equal to f of 3y. If I substitute 3y, I have floor function of 3y over 3. That's the floor function of y. Since y is an integer, floor function of y is the same as y. So f is onto. And we don't need this. This is your scratch work. We use this to find x. That's your scratch work. That's not a part of proof. Next, we will study bijection. First of all, let me introduce what's a bijection. If a function is one-to-one and onto, if a function is one-to-one and onto, then we say the function is a bijection. If a function is one-to-one and onto, then we say the function is a bijection. Bijection is the same as one-to-one correspondent. If a function is one-to-one and onto, then we say the function is a bijection or a one-to-one correspondent. One-to-one correspondent is the same as saying bijection. Next, let's do some example about bijection. For each of the following functions, determine whether it's a bijection. For each of the following functions, determine whether it's a bijection. First example, let f from real number to real number be defined as f of x equal to s cubed minus 1. Is this function a bijection? Is this function a bijection? If a function is bijection, we must show the function is one-to-one and onto. But if the function is not one-to-one or not onto, then it's not a bijection. Is this function one-to-one or onto? Is this function one-to-one and onto? If f assign every element in the domain to a different element in the codomain, then the function is one-to-one. But if f assign any two elements in the domain to the same element in the codomain, then f is not one-to-one. Let's try some examples. If I substitute 0, I get -1. If I substitute 1, I get 0. If I substitute 2, I get 7. It looks like f assign every x in the domain to a different value, to a different element in the codomain. So it looks like the function is one-to-one. Is the function onto? If the codomain is the same as the range, then the function is onto. The codomain here is the set of all real numbers. Is the range also all real number? X can be any real number. If I substitute some very, very large positive number, I get positive infinity. I guess the function goes to positive infinity. If I substitute some very, very large negative number, the function approaches to negative infinity. So it looks like the range is also the set of all real numbers. So it looks like the function is one-to-one and onto. So let's try to prove the function is a bijection. Let's first of all show that the function is one-to-one. So let S1, x2 belong to the domain. I will show you the function is one-to-one. So let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. Assume f of S1 equal to f of S2. Then I substitute S1 into the function. I substitute S2 into the function. I have S1 cube minus 1 equal to s2 cube minus 1. Add 1 to both sides, I have s1 cube equal to s2 cube. Then I can take cube root on both sides. Take cube root on both sides. I have s1 equal to s2. If I take cube root on both sides, I get s1 equal to s2. So f of s1 equal to f of s2 implies s1 equal to s2. That means f is 1 to 1. Is f a onto function? Is f a onto function? We just verify that the codomain is the same as the range. So it looks like the function is onto. Let's try to prove it. To prove onto, let y belong to the codomain. We try to use definition to show a function is onto. So for all y in the codomain, there's x in the domain such that f of x equal to y. Let y belong to the codomain. We try to find an x. Let's make f of x equal to y. So we want to make f of x equal to y. F of x is s cubed minus 1. So I can solve the equation for x. S equal to y plus 1. S cubed equal to y plus 1. S equal to cube root of y plus 1. And for any real number y, cube root of y plus 1 is always a real number. So let x equal to cube root of y plus 1. That's always a real number. For all y, let s equal to cube root of y plus 1. Then f of x equal to f of cube root of y plus 1. For f of cube root plus 1, y plus 1, I substitute this into the function. I have cube root of y plus 1 cube minus 1. Cube root cancels, power 3 cancels cube root. I have y plus 1 minus 1, which equal to y. So for all y in the codomain, there's an x in the domain such that f of x equal to y. So f is onto. Since f is 1 to 1 and onto, therefore I can say f is a bijection. If a function f is 1 to 1 and onto, then we say the function is a bijection, or is a 1 to 1 correspondent. Next, let f from real number to real number be defined as f of x equal to s cubed minus x. Is this function a bijection? So let's first of all check if the function is 1 to 1 and onto. Is this function 1 to 1? If the function f assign every element in the domain to a different element in the codomain, then f is 1 to 1. But if f assign any two elements in the domain to the same element in the codomain, then f is not 1 to 1. Let's try to plug in some numbers first. If I substitute 0, I get 0. If I substitute 1, I also get 0. So if f assign two elements in the domain to the same element in the codomain, f is not 1 to 1. Since f is not 1 to 1, f is not a bijection. So let's first of all prove f is not 1 to 1. So let x1 equal to 0, s2 equal to 1 in the domain. Then f of s1 equal to f of 0, which is 0 cubed minus 0, which is 0. F of x2 is f of 1, which is 1 cubed minus 1, also equal to 0. Since f of s1 equal to f of s2, but s1 doesn't equal to s2, then f is not 1 to 1. Since f is not 1 to 1, f is not a bijection. Therefore, f is not a bijection. Another example. Let f from integer to integer be defined as f of x equal to 5x plus 2. Let f from integer to integer be defined as f of x equal to 5x plus 2. Is this function a bijection? So to show a function is bijection, we try to show that the function is a 1-to-1 and onto. Is this function 1-to-1? If f assign every element in the domain to a different element in the codomain, then f is 1-to-1. But if f assign any two elements in the domain to the same element in the codomain, then f is not 1-to-1. So let's try to plug in some numbers here in the domain. If I substitute 0, I get 2. If I substitute 1, I get 7. If I substitute 2, I get 12. So it looks like this function f assign every element in the domain to a different element in the codomain. It looks like the function is 1-to-1. It looks like the function is 1-to-1. Is the function onto? Is the function onto? If the codomain is the same as the range, then the function is onto. If the codomain is not the same as the range, then the function is not onto. The codomain is here, it's the set of all integers. What's the range? What's the range? If I substitute 0, I get 2. If I substitute 1, I get 7. If I substitute 2, I get 12. It looks like between two numbers, between two consecutive numbers, f skip a lot of numbers. F cannot be 3, 4, 5, 6. If I plug in 0, I get 2. Plug in 1, I get 7. It looks like the function skip 3, 4, 5, 6. It looks like the function skips 3, 4, 5, 6. That means the function cannot be 3, 4, 5, 6. So the range is not the same as the codomain. So that means f is not onto. If f is not onto, it won't be a bijection. So let's try to prove the function is not onto function. To show a function is not onto, we give an example. So let y equal to, for example, 3 in the codomain. We know this function cannot be 3. If I plug in 0, I get 2. If I plug in 1, I get 7. It skips 3 here. So it looks like the function cannot be 3. So let y equal to 3. Assume f of x equal to 3. Then we have 5x plus 2 equal to 3. So if I solve for 3, 5x equal to 1, and so x equal to 1/5. Assume f of x equal to 3, then 5x minus 2 equal to 3. Subtract 2 from both sides, 4s equal to 1, so s equal to 1/5. But s is an integer. Domain is integer. That's impossible. 1/5 is not in the domain, that's impossible. So f of x doesn't equal to 3. and 3 is y. So it's f of x that's equal to y for all x in the domain. So f of x that's equal to 3. That means f of x that's equal to y for all x in the domain. So f is not onto. Since f is not onto, f is not a bijection. Since f is not onto, f is not a bijection. So keep in mind, if f is a bijection, it must be 1-to-1 and onto. If f is either not 1-to-1 or not onto, if f is either not 1-to-1 or not onto, f is not a bijection. If f is a bijection, it must be both 1-to-1 and onto. Next, let me introduce inverse function. Let f from a to b be a function. If f is 1-to-1, then there exists a function g from from the range of f to a, such that g of y equal to x for all y in the range with f of x equal to y. And this function g is called the inverse function of f. Denoted by f inverse. Let me show you an example. Let A be the set of A, B, C, for example. Let B be the set of A, B, C, D, E. F is a function from A to B that assign A to B, f assign B to C, f assign C to D. Then BCD here, the set of BCD is the range of f. The set of BCD is the range of f. F assign A to B, B to C, C to D. So the set of BCD is the range of f. The inverse function, f inverse function map from range of f to A, to the domain of f. Range of f is B, C, D. Domain of f is A, B, C. So inverse function of f assign B back to A, assign C back to B, assign D to C. That's an inverse function. F assign A to B, B to C, C to D. The inverse function assign B to A, assign C to B, assign D to C. That's called the inverse function. Note, if f is a bijection, then there is this inverse function. There's an inverse function mapped from B to A. Assume f is from A to B. If f from A to B is a bijection, then there exists inverse function from B to A. If f is a bijection, then the range of f is the same as the codomain of f. F of A is the same as B. If f is a bijection, then f is onto, then f of A is the same as B. So if f is a one-to-one, then there's inverse function from f of A from the range f of A to A. If f is a bijection, then there's inverse function from B to A. Next, let's look at some example about inverse function. Let f from the interval 4 to infinity to all real number be defined as f of x equal to square root of x minus 4. Verify let f is one-to-one and then find its inverse function. So first of all, let's verify that f is one-to-one. Let S1, S2 belong to the domain assume f of S1 equal to f of S2. That means square root of x1 minus 4 equal to square root of s1, s2 minus 4. If I square both sides, s1 minus 4 equal to s2 minus 4. Add 4 to both sides. I get x1 equal to x2. So f is 1-to-1. Next, we try to find the inverse. To find the inverse function, we first want to find the range first. We need to find the range first. Inverse function is go from the range back to the domain. We need to find the range first. Inverse function map from the range back to the domain. How do we find the range? If we substitute 4, we get 0. If we substitute 5, we get 1. If I substitute infinity, eventually the number approaches infinity. So the range is from 0 to infinity. That's the range. We can see that if I substitute 4, I get 0. If I substitute 5, I get 1. It's increasing. If I substitute 6, I get square root of 2. Eventually, if I substitute a very, very large number, f of x becomes very, very large. So the range is from 0 to infinity. Inverse function map from the range back to the domain. Keep in mind, inverse function map from the range back to the domain. Inverse function map from the range to the domain. Then, how do we find the inverse function? We treat y equal to f of x. First of all, we let y equal to f of x. Let f of x equal to y. Then solve an equation for y. Square root of x minus 4 equal to y. square both sides. S minus 4 equal to y squared. Solve the equation for x. X equal to y squared plus 4. So the inverse function of y is y squared plus 4. That's how we find the inverse function. But in general, we try to write it in terms of x. So we write inverse function of x equal to x squared plus 4. They are the same. You can write it as inverse function f of y equal to y squared plus 4. Or you can write the inverse function of x. Inverse function f of x equal to s squared plus 4. They are the same. That's the inverse function of f. So to find the inverse function, there are 3 steps. You first of all verify the function is 1-to-1. That's the first step. Then you find a range. Inverse function must go from range to the domain. You find a range. Then you set f of x equal to y. Solve an equation for x. That's your inverse function. Or you can write it in terms of x. So either way is okay. That's the third step. First step, verify f is 1-to-1. Next, find a range. Then you find the inverse function. Another example. Let f from real number to real number be defined as f of x equal to 2x plus 1. Verify that f is 1-to-1 and find its inverse function. So first of all, verify f is 1-to-1. Assume x1, s2 belong to the domain. If assume there are s1, s2 belong to the domain, so let s1, s2 belong to the domain. Assume f of s1 equal to f of s2. Then substitute s1, substitute x2. We have 2x1 plus 1 equal to 2x2 plus 1. We try to show s1 equal to s2. So I can subtract 1 from both sides. I get 2s1 equal to 2s2. Then I divide both sides by 2. I have s1 equal to s2. So f is 1-to-1. Next, to find the inverse function, we need to first of all find the range. Inverse function map from the range to the domain. The domain is the set of all real numbers. The domain is the set of all real numbers. How do we find the range? If I substitute 1, I get 1. Substitute 2, I get 3. Substitute 4. Substitute 3, I get 5. Substitute 3, I get 7. So it looks like if I substitute very large x, I get very large positive number. If I substitute very large negative number for x, I get very large negative number. So it looks like the range is the set of all real numbers. It could be very large positive number. It could be very large negative number. So the range is the set of all real number. Now to find the inverse function, we set f of x equal to y. F of x is 2s plus 1. Solve the equation for x. 2s equal to y minus 1, s equal to y minus 1 over 2. So inverse function, I can write f inverse of y equal to y minus 1 over 2. Or I can write f inverse of x. Sometimes we write it in terms of x equal to x plus x minus 1 over 2. Either way is okay. Now be very careful with one thing. In the same textbook, the same chapter, this symbol was used for 2 different things. In the earlier chapter, it was used to express the inverse image of an element under F. And now it's also be used to express the inverse function F. This symbol has two different meanings. If we look at if this example says let F be a function from real number to real number, the F from real number to real number be defined as f of x equal to s cubed. Find f inverse of, for example, f inverse of A. What should we do? This f inverse, it may represent the inverse image of element A. It may represent the inverse function of f. Now what should we do? So two things. First of all, verify if f is 1 to 1. If f is not 1 to 1, then f is not invertible. Its inverse function doesn't exist. It must mean inverse image of an element. If f is not 1 to 1, then f is not invertible. Its inverse function does not exist. It only represents inverse image of an element. But what if f is 1 to 1? What if f is 1 to 1? Then let's check first. Is f 1 to 1? Let's check. Let S1, S2 belong to the domain. Assume f of S1 equal to f of S2. Then we have plugging. We have S1 cube equal to S2 cube. If I take cube root on both sides, I have S1 equal to S2. So f is 1 to 1. If f is 1 to 1, then f inverse exists. So f inverse exists. So the inverse function exists. Let's find the inverse function. The range is also the set of all real numbers. Let's find the inverse function. We treat f of x equal to y, s cube equal to y, s equal to cube root of y. So if the inverse function equal to cube root of y, we can also write it as inverse function of x equal to cube root of x. So if we treat f inverse of A, if we treat f inverse as an inverse function, as the inverse function of f, then f inverse of A is cube root of A, that equal to 2. If we treat f inverse as the inverse image of an element under F, then F inverse of A, the inverse image of A, can be written as the set of all x in the domain, the set of all x in the domain, such that f of x equal to A. That's the set of all x in the domain such that s cubed equal to A. If we solve the equation, only 2 satisfies this equation, so that's the set of 2. So if f is 1 to 1, there's no big difference. You can say f inverse of A is an element, is number, is element 2, or it's a set of 2. There's no big difference. If we treat inverse f is an inverse function, then answer is number 2. If we treat this as inverse element, inverse image of an element, then answer is the set of 2. There's no big difference. Either way is acceptable. Another example, let f from real number to real number be defined as fx equal to x squared. Find f inverse of 9. Now, first of all, let's verify is f 1 to 1. Let's verify is f 1 to 1. If I substitute negative 1, I get 1. If I substitute 1, I also get 1. So f is not 1 to 1 function. Let s1 equal to negative 1, s2 equal to positive 1 in the domain. F of x1 equal to f of negative 1 equal to negative 1 squared equal to 1. F of s2 equal to f of 1 equal to 1 squared, which is also 1. Since f of s1 equal to f of s2, but s1 is not the same as s2, then we know f is not 1 to 1. Since f is not 1 to 1, then so the inverse function f inverse does not exist. Since the inverse function does not exist, then this must represent the inverse image. So f inverse, it must represent the inverse image. F inverse of 9 is the set of all x in a domain. It's the set of all x in a domain such that f of x equal to 9. That's the set of all x in a domain such that x squared equal to 9. If you solve the equation, s could be either positive or negative 3. So inverse image of 9 is the set of negative 3 and positive 3. This only represents inverse function. F is not invertible. It doesn't represent inverse function. It only represents inverse function. Sorry, I mean only represent the inverse image at 9. It only represents inverse image at 9, which is negative 3 and 3. So if a function is not 1 to 1, this symbol only represents inverse image. But if the function is 1 to 1, there's only one element in the set. So there's no difference of treating this as inverse function or inverse image. There's no difference. Next, let me introduce composition of functions. Let f from A to B and g from B to C be functions. The composition function g of f from A to C is defined as g of f of x equal to g of f of x for all x in A. Let me show you the diagram. It makes more sense. Let me show you an example in diagram. Assume A is the set of A, B, C, D. Assume B is the set of 1, 2, 3. Assume C is the set of triangle and star. F is a function from A to B. G is a function from A to C. Assume f assign A to 1, B to 2, C to 2, and D to 3. Assume G assign 1 to triangle, 2 to star, 3 to star. The composition function g of f of A by definition is g of f of A. F assign A to 1, so f of A is 1. F of A is 1. And g assign 1 to triangle. G of 1 is triangle. So g of f of B g of f of B is g of f of B. F of B, f assign B to 2, so I get g of 2. G of 2 G assign 2 to star. G of f of C, that's g of f of C. F assign C to 2, so I get g of 2. G of 2, G assign 2 to star. Then the last one, G of f of D. That's by definition, that's G of f of D. F of D is number 3, and G assign 3 to star. So G of f is a function from A to C. A is in the set A, B, C, D. C is in the set triangle, star. This function assign A to triangle, assign BCD to star. That's the composition function of G of f. Next, let's look at an example. Let f, functions f and g, from real number to real number be defined as f of x equal to 2s plus 1 and g of x equal to s cubed minus 1. Find the composition function f of g and g of f. Let's compute f of g first. F of g of x is defined as f of g of x. G of x is s cubed minus 1, which is, I substitute s cubed minus 1 into function f. That's 2 times s cubed minus 1 plus 1, which is 2s cubed minus 2 plus 1 equal to 2s cubed minus 1. G of f of x is g of f of x, that equal to g of 2s plus 1. So we substitute 2s plus 1 into function g. We have 2s plus 1 cubed minus 1. If we simplify the function, I have as cubed plus 12x squared plus 6x plus 1 minus 1, that equal to as cubed plus 12s squared plus 6x. That's the competition functions. But keep in mind that in general, f of g, the competition functions f of g and g of f is not the same. In general, the competition function g of f and f of g, they are not the same. Next, let me introduce the property of inverse function. Let f from a to b be a one-to-one function, and let inverse of f from the range of f to the domain of f be its inverse function. Then f of f inverse of y equal to y for all y in f of a, in the range of a, and f inverse of f equal to x, f inverse of f of x equal to x, or for all x in a domain. Let's prove it. Let x belong to a, and f of x equal to y. Then f inverse of y equal to x. That's the definition of inverse function. So let's prove the first statement. F of f inverse of y, by definition of competition function, that's f of f inverse of y. F inverse of y is x, and f of x is y. F inverse of f of x, that's f inverse of f of x. F of x is y. F of x is y. F inverse of y is x. Next, let me introduce a theorem. If function f from a to b and function g from b to c are one-to-one functions, then the competition function g of f from a to c is also one-to-one. Let's prove it. Let's try to prove it using definition of one-to-one function. Let k be the function of g of f. To show k is one-to-one, we need to show that for all s1, s2 in A, k of s1 equal to k of s2 implies s1 equal to s2. Let's go try to prove this. So let k equal to the composition of g and f, g of f. Let s1, s2 belong to A. Assume k of s1 equal to k of s2. We try to prove s1 equal to s2. Assume k of s1 equal to k of s2. Then g of f of s1 equal to g of f of s2. Then g of f of s1 equal to g of f of s2. Since g is one-to-one, then we know that g of, for example, g of square equal to g of triangle implies triangle equal to rectangle, so square equal to triangle. Since g is one-to-one, then we know that g of anything here, g of anything here, g of square equal to g of triangle implies square equal to triangle. So similarly, g of f of s1 equal to f of s2 implies f of s1 equal to f of s2. So we have f of s1 equal to f of s2. Since f is one-to-one, then f of s1 equal to f of s2 implies s1 equal to s2. F of s1 equal to f of s2 implies s1 equal to s2. So we have s1 equal to s2. Since k of s1 equal to k of s2 implies s1 equal to s2, then therefore k equal to g of f is one-to-one by its definition. Similarly, there's another theorem that says if f from A to B and g from B to C are onto functions, then g of f from A to C is also onto. Let's prove it using definition of onto functions. Proof. Let k equal to g of f. If I want to prove it using definition of onto function, I want to show that for all z belong to C, for all z belong to C, there is an x in A. there is x in A such that k of x equal to z. So that's what I want to prove. So let z belong to C. Since G is onto, since G from B to C is onto, then there exists a y in B such that G of y equal to z. Since y belong to B and f from A to B is onto, then by definition of onto function, there is x in A such that f of x equal to y. Then I can say that for all z belong to C, there is a x in A such that k of x equal to g of f of x equal to g of f of x. F of x is y. F of x is y, so I get g of y. And g of y equal to z. Let's complete the proof. This proof says for all C in Z, there is a x in A such that k of x equal to z. For all z in C, there is x in A such that k of x equal to z. Let's complete the proof. Therefore, k equal to g of f is onto. So these two theorems says the composition of one-to-one function is one-to-one, and the composition of onto function is onto. Based on these two theorems, there's a corollary. Says the composition of bijection functions is bijection. The composition of bijection functions is also bijection. That's the corollary. If f from A to B, g from B to C are bijections, then the composition function g of f from A to C is also a bijection. Let's prove it. This proof is very simple. Since f and g are bijections, then f and g are both one-to-one and onto. Since f and g are bijections, then f and g are both one-to-one and onto. Since f from A to B and g from B to C are one-to-one, then g of f is one-to-one by the first theorem. Since f from A to B, g of f is from A to C, is also one-to-one. Since f from A to B and g from B to C are onto function, then by the second theorem, g of f from a to c is also onto function. Therefore, since g of f is one-to-one and onto, g of f is a bijection. So that's the proof that says composition of two bijection functions is a bijection. The composition of two bijection functions is a bijection.